Welcome back to Astronaut. Today we're talking about Blackbody radiation.
I feel like an astronaut in what you know about rolling down in the deep.
All objects that have a temperature, that is, anything above 0 Kelvin, emit electromagnetic radiation. Stars emit energy in all wavelengths, but they emit more energy at a particular wavelength than at other wavelengths. The exact distribution of radiation emitted is dependent on an object's energy, which is in turn dependent on the object's effective temperature. Hot objects emit radiation at high frequencies. Stars like the Sun, at a temperature of around 5,800 Kelvin, have a radiation distribution that peaks in the visible regime. Hotter stars can peak in the ultraviolet regime. A black body is a theoretical model of an object that both absorbs and emits all incoming or outgoing electromagnetic energy. That means no energy is transmitted or reflected off of the body. We often approximate stars as black bodies for calculation estimates, even though they are not perfect absorbers or emitters. We can model a black body with Planck's law. Planck's law relates wavelength to spectral energy density and describes the shape of a black body. The wavelength at which this curve peaks can be derived by finding where the derivative of Planck's law equals 0. That's a good exercise, but fortunately Wilhelm Wien removed much of this hefty derivation with his correlation between peak wavelength and temperature, Wien's displacement law. He actually came up with the formula theoretically, but Wien's displacement law can be derived directly from Planck's law. The Sun has a surface temperature of 5,800 Kelvin. At what wavelength does its flux peak? If we divide 5,800 Kelvin from 2.898 e to the negative third meters, we calculate a peak wavelength of 500 nanometers. 500 nanometers is in the visible regime, which is exactly what we'd expect for the Sun's radiation. Okay, so after all this, remember we said stars aren't perfect black bodies? That's because, in reality, stellar atmospheres are full of atoms and ions that play a role in the absorption and emission processes. The Sun's spectrum is tainted with absorption lines from elements like hydrogen and helium, which we can see as deviations from its idealized blackbody curve. The interplay of the blackbody continuum spectrum and diffuse gases yields the actual absorption spectrum we detect. As always, thanks for tuning in. Ponder, wander, and go right in the stars.
Slow